Okay, so one thing for the master students, I only receive a few list of papers. So what I propose is if you could write on a piece of paper what you want, and like that, while you are correcting the exercises, I will try to make some kind of list and we can discuss just after for 10 minutes who has what, okay? Just before we start, to go back, because I did kind of messed it up a little bit. What you finish and how you prove that you have only that you have less than the size of the boundary number of trifurcations in the thing. So let me just redo it like that. We all have it. So let's say this is a trifurcation here. This is a trifurcation, and this is one. Let's say this goes to infinity. So the first thing, so you only look at what is inside the box, and you do that. First, all the cycles, let's say you index all your edges in your box. In all the cycles, there is one edge which has the smallest numbering. Just kill it. Okay, so let's say here it's this edge, you kill it. Here it's this edge, you kill, 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 kill. So when you do that, what you get is a tree now. You killed all the cycles in this box, right? So you have a tree. Now in this tree, kill all the pieces which are not going to infinity. So as soon as there is one of the endpoints which is not connected to infinity in an edge, you remove it. So you kill this. You kill this, I guess. You kill all these guys. So let's say these guys do not go to infinity. You kill really everybody and so on. And so what you get at the end is a tree where anyway, if you remove an edge, I mean, as soon as you have an edge, both endpoints are connected to infinity. Okay? So the leaf in particular of this edge have to be on the boundary. They cannot be inside because otherwise one of the ends will not be connected to infinity. Okay? So all the leaves are on the boundary. And now all the trifurcations are still there. You never deleted them. I mean, you never deleted the fact that they are connected by three pieces to infinity. Therefore, the trifurcations are exactly the point with degree larger or equal to 3 in your tree. So there are less trifurcation than leaf. So there are less trifurcation than points on the boundary. Okay? That was just a parenthesis because it was not so precise when I did it last week. Okay, so we finished on this lemma, remember, which we can basically say is dating back to Harris, which is saying that if I define this phi p of s, which is p times the sum for x, for xy in delta s, in the boundary, in the edge boundary of your graph, of the probability that 0 is connected to x in S. So it's, roughly speaking, the expected number of points on the boundary which are connected to 0, except that you have this time p and you count with multiplicity. And remember we said, okay, if I can find one S, just one, for which this thing is smaller than 1 strictly, then I have exponential decay. And I told you if you apply that to S, which is just the singleton equal to 0, then you recover exactly this argument using just Peirce's argument, counting of path. But you can extend it to any set S containing 0. So let's define PC tilde to be the infimum of the P such that phi P of S is larger or equal to 1 for every S finite and containing 0. I can define this quantity. And I have, so notice I have that for P strictly smaller than PC tilde, there exists a constant C such that I have exponential decay. Right? Because simply for any p smaller, I will find a S which phi p of S is smaller strictly than 1. So my goal now is to prove that PC is equal to PC tilde. So there is one inequality which is clear. Which one? Well, PC tilde, it has to be smaller or equal to PC. That's clear. Simply because below PC tilde, I don't have an infinite cluster. So my only goal now is to prove that PC tilde is larger or equal to PC. And how can I do that? I can do that by proving that for any P larger than PC tilde, sorry, what am I? Yeah. For any P larger than PC tilde, I have an infinite cluster. So I'm going to fix P larger than PC tilde and try to prove that. How do we do that? Well, what we are going to try to use is the properties of monotonicity of my percolation. I'm going to try to just take, for instance, the probability that 0 is connected to distance n, and try to find a differential equation satisfied by this quantity. And see that this differential equation forces it to blow up above PC tilde. Okay? So this is something, in fact, the original proof of Eisenman and Barsky and Menshikov, they all use somehow some kind of differential inequality. And you should not be too much surprised by this fact, because if you think about it, this, for instance, the probability that 0 is connected to infinity, that's so theta of p, you can see it as the density of your medium. So when you are taking a differential inequality on this, you are taking a differential inequality on what we call a thermodynamical quantity of your system. And if you did a little bit of thermodynamics in physics, you will notice that it's always about differential inequalities, relation between different thermodynamical quantities. You know, the pressure, the volume, the temperature, all these things, you relate them, you mix them, and you get a relation between them using the differential inequalities. Well, it's a little bit what we are doing in our context. So this approach is very physical in nature. So the lemma is going to be the following. It's going to say that for any P larger or equal to PC tilde, I have the following, and for every n, and for every n larger or equal to 1, I have the following differential inequalities. The derivative of the probability that 0 is connected to the boundary of the box of size n is larger or equal to 1 over p 1 minus p times 1 minus the probability. So here, I mean, don't really try to understand why this is a natural differential inequality. I mean, before this proof, it was never used anywhere, so it's not like it's so natural somehow. You are going to see that when you do the proof, it's not completely crazy, but somehow the intuition behind this differential inequality really comes from the fact that we want to use this phi p of s. So let's not bother too much about the intuition. Let's see what it does to us. Imagine you have that for any p larger than PC tilde, larger or equal to PC tilde. Then, what can you deduce? Well, you can deduce from that, just integrate. So imagine, I mean, set f of p to be the probability that 0 is connected to the boundary of the box of size n. Here you get what? You get f prime of p larger or equal to 1 over p 1 minus p 1 minus f of p. Right? So you can see it as f prime of p over 1 minus f of p 1 over p 1 minus p. Now this is what? This is the derivative of the log of 1 minus f of p. Right? And this is larger or equal, and this is the derivative of something like log of p over 1 minus p or something like that. So you integrate this guy between p and PC tilde and PC and p. So integrate between PC tilde and p to find. What do we find when you do that? Well, let's forget a little bit about the details of the computation. I mean, you can do them by yourself. And you find that f of p is larger than p minus pc tilde over p 1 minus pc tilde. That's what you find. Just the integration of the guy above. So notice here, there are a few interesting facts about that. The first one is that in addition to tell you that it's going to be positive above pc tilde, which anyway we knew, right? I mean, this is probability which is positive anyway. It's independent of n. The bound here doesn't depend on n. So I can let n tends to infinity. So as n tends to infinity, I get that the probability this time that 0 is connected to infinity is larger than p minus pc tilde over p 1 minus pc tilde. So in particular, this is also strictly positive if p is larger than pc tilde. Okay? So if I'm able to prove this lemma, then I'm done. Notice another thing which is interesting here. This, how does it blow up when p is larger than pc? So if p is larger than pc tilde, therefore, in particular, pc tilde has to be larger or equal to pc, and therefore that pc equal pc tilde. So I finish my theorem if I do that, and I have this kind of neat inequality, which is here, the probability that 0 is connected to infinity, it blows up, it's larger than a constant times p minus pc, in fact. Right? This is always smaller than 1, so all of this is small. Oh, I could even write it like that, for instance. The important thing here is that when you draw in terms of p, the probabilities that 0 is connected to infinity, so there is a pc, there is 1. So it's 0 up to a certain value, which is pc. And then I have no clue what it is, but I know it is larger than, in fact, it's larger than a line like that. So it's actually, maybe it actually starts here and does something like that. Maybe it starts here, but then it's not differentiable, for instance. So if it starts here, it will have to be above. So this is what we call a mean field lower bound on the blowing. So the probability that 0 connected to infinity is larger than p minus pc is a mean field lower bound. And the reason for calling it like that is that, in fact, if you look on a tree, that's a nice exercise. Try to study percolation on a tree. And you're going to see that, in fact, it blows up exactly like p minus pc times a constant on the tree. And so, because this is, this quantity blows up like p minus pc on a tree. And in fact, an even more interesting property is that it's going to be the same for, in fact, any zd with d larger than 6. So if you are in sufficiently high dimension, it blows up like p minus pc. So this bound, which can seem to be very just rough and not so precise, in fact, it gives you the right order of magnitude if you are on a lattice, a hypercubic lattice with d large enough. I think there is something kind of magical about that. If you take a large lattice, a lattice in large dimension, it basically, from the point of view of statistical physics, it behaves like the tree. It's like the cycles are so big, but they are not really, they are big, but they are still finite size, that from the point of view of physics, there is sufficient room in your lattice that you don't feel the cycles, that you look like something on a tree. Okay, so this is a mean field lower bound. It's always nice to have a mean field lower bound, because then you need only to prove the other inequality if you want to prove mean field lower behavior. I should tell you a little bit more, and maybe actually I'm going to, maybe I will even do it, I don't know. If you are in dimension 2, in fact, this is not the truth. The P minus PC is not the right behavior. You will do it probably in second semester. You will see that it's P minus PC to the 5/48, the right behavior. 5/36, sorry. So it's not P minus PC to the 1. So in 2D, it behaves like that, really. And in particular, it has, here, a blow-up of this type. So it's not the truth in any dimension. Last thing I want to say, okay, in 2D you will be able to prove this behavior, very nice for you. In 3D, 4D, 5D, and actually 6D and 7D, and until, so this is actually not proved up to 6, it's proved up to 11 now. It was proved up to 19 a few years back, but now it's 11. In the intermediate dimension where we don't know how to prove this type of things, we don't even know that this is 0. We don't even know that there is no infinite cluster at criticality. So this is far from a sharp bound. We expect it's the case, but we don't know how to prove. Okay, this was all of, not useful for the proof, what I said. So let's now finish the proof of our theorem by proving this lemma. How do we do that? Well, let's go pedestrian somehow and say, okay, this, I know how to write it, d over dp of the probability that 0 is connected to the boundary of the box of size n. This is just the sum in the edges of lambda n of the probability that E is pivotal for 0 connected to the boundary of the box of size n. Okay? This is just Rousseau's formula. Now, remember also that I told you that being pivotal doesn't depend on the state of the edge E. Right? Because anyway, you change the state in the definition to check whether you are pivotal or not. So I'm going to force the edge to be closed. Because being being pivotal is dependent of the state of the edge. Asking that it's closed, it's like just asking 1 over 1 minus p, sum over the edges. And just say, okay, E is closed and E is pivotal for 0 connected to the boundary. I just use the dependence. This is now 1 minus p. It cancels with this 1 minus p. This is an equality. Okay. So remember, I have 0 here. This is the boundary of your box. Remember that being pivotal is basically an edge is going to be pivotal here. Let's say this is the edge xy. If it's connected like that, and if it's closed, there is this kind of hypersurface of closed edges, which is blocking the existence of a path from the middle to the boundary. Just here when I said xy is an edge, I didn't tell you who was x, who was y, so here I'm going to just take that x is connected to 0 and y is connected to the boundary. Okay? So this is the event that the edge is pivotal. So notice something nice, which is y is always connected to the boundary and 0 is not. So what I could do is I could decompose along the following. Let's define S to be the set of X or Z in my box such that Z is not connected to the boundary of the box. So these are the guys that are not connected to the boundary. And here I can in this inequality, I can just decompose into the possible values for S. So this is 1 over 1 minus p. I'm going to use the whole line. So it's 1 over 1 minus p. I'm going to decompose on the set S, the possible values of the set S for capital S. And notice that here I said E is closed and E is pivotal. So what can I say about the event that 0 is connected to the boundary? It doesn't occur, right? Because E is closed. So in addition, the possible value for S is going to be, I can always assume that 0 is in S. This is a small parenthesis, but 0 is in S. And here I write the sum over x and y in the edges of lambda n. And I'm going to just write, so E is closed, E is pivotal, let's just write it like that, and S is equal to S. Are you all okay with this decomposition? It's a part, this is the sum of all the S, it's just a partition of this thing. So I'm just writing the same thing. Okay, but now I know that the set of points which are not connected to the boundary is a certain set S. Let's call it S like that. Maybe it has holes, I don't know, but it's a set like that. What are the possible xy satisfying that, if I know that S is equal to S, the edge xy, so E is the edge xy. Should I be a little bit more precise here? What are the possible xy for which this probability is positive? Well, let's take an edge like that. Let's take an edge which is not on the set of S which are not connected. So let's forget about this thing now. I take this edge, E, and let's assume that the 2 points are outside of S. What does it mean to be outside of S?
To be connected to the boundary?
That means that we are connected to the boundary. The 2 guys are connected to the boundary. Okay. Maybe they are connected like that, by the way. Maybe it's like that. But anyway, here, this closed surface, which is blocking, so if this is S, by definition, it's not connected to the boundary, so there is a closed surface like that. Whatever the state of the edge is, this closed surface is here. And it's blocking the fact that this guy is connected to 0. That 0 is connected to the boundary, sorry. So whatever the state of this edge, 0 will never be connected to the boundary. So this guy cannot be pivotal edge. And this is the same if I take an edge where 2 guys are inside S. Because that means that this closed surface will remain closed anyway, whatever the state of this edge. So the only possible behavior is that one of the points is inside, and basically that the edge is crossing this closed surface. So let's call X the guy inside, Y the guy outside. So like that, I know anyway that if it's closed, I'm not connected to the boundary. This I know already, because it is on this closed surface. Now I need to check that if it's open, I am connected to the boundary. Y is not in S. So Y is connected to the boundary, by definition. So I have nothing to do with that. But now if I want this edge to be pivotal, I need that if this is open, then there is a path from 0 to the boundary. But because there is this closed surface, this path has to go through X. There is no choice otherwise. So if I want the edge xy to be pivotal, I need it to be on the boundary of S. But I also need that X is connected to 0 in S. So this thing I can rewrite. So this is exactly the same. So I can rewrite as sum over S in 0. Now I can look at the edge xy just on the boundary of S. It needs to cross the hypersurface. The fact that the edge is closed now comes for free if I know that S is equal to S, because otherwise that would mean that Y I mean, since y is connected to the boundary, x would also be if the edge was open, sorry. So this, I can just ignore it. And being pivotal here, we said, well, if we are on the boundary, the pivotal points are exactly the guys for which x is connected to 0. So here, I can rewrite this whole probability like that. Good? Now, what do we need to do now? Well, here, what is the state of the edges that I need to know to decide that S is equal to S? What information do I need? Well, I need everything which is outside of S or on this hypersurface. So I need to know all the edges with at least one endpoint outside of S. So this is measurable in terms of edges with one endpoint outside of S. What do I need to know whether 0 is connected to S, to X in S? Well, because it's in S, I only need to know the state of edges with both endpoints in S. So this is measurable in terms of edges with both endpoints in S. So they depend on different state of edges. By independence, I can just say that this the product of the probability of the intersection is just the product of the probabilities. So here I can write the sum over the edges xy of the probability of 0 connected to x in S times the probability that S is equal to S. This is what? Well, this is 1 over p times phi p of S. So this is 1 over p, 1 minus p, the sum over S in 0. And here I get, so this is 1 over p phi p of S. So since I am above pc tilde, this is larger or equal to 1 over p. So I get the 1 over p, and I just get the probability that, that S is equal to S. Is it clear for everybody what I did here? So I made this phi p of S appear. And I'm using that this is here, this is due to the fact that p is larger than pc tilde. Can somebody tell me what is this quantity? I'm summing over every set which do not contain 0 the probability that the set of points not connected to the boundary is S. So what is it?
The probability of being connected.
It's exactly this. These guys are partitioning one event, which is very simple to see, which is 0 not connected to the boundary. This is a partition. If I sum on every S like that, this is partition of this set. So this big sum, so I have a 1 over p, 1 minus p. And this is just the probability that 0 is not connected to the boundary of the box, which is 1 minus the probability of being connected. So I'm done. Okay? So there, I didn't hide anything. This is a full proof. And you see, the fact that you get this, oh, okay, so here, I mean, you can write like that if you want. The form of the differential inequalities that you get here really comes from basically just trying to see how many pivotals you have and just constructing the pivotal manually somehow, by hand. By just saying, okay, so I use, this is just mechanical, it's just saying I use Rousseau's formula. And here now, I mean, to count the number of pivotals, what I do is that I just gather them depending on what is the surface of the exterior-most blocking surface somehow. So I condition on this blocking surface, and now I say, okay, conditionally on that, how many pivotal do I have? The answer is phi p of s. Yes?
Didn't we obtain equality instead of inequality?
So it's not an
inequality.
Here, it's an inequality. Yeah, thank you. So here, I mean, phi p of s is larger or equal to 1 over p. And actually, in many cases, it's going to be much larger. In dimension 2, it's going to be much larger. In dimension d with d very large, well, in average, it's going to be basically 1. So it's going to be almost an equality. Here it's an equality, basically, up to constant, say. That doesn't mean that the phi p of s is always basically 1 at criticality. It just means that typically it is. For typical set S like that, you get that the phi p of s is roughly of order 1. Okay? So this is a proof of exponential decay. And there are many applications of that. So I mean, I put some of them in the exercise session. I'm sorry, I mean, there are people who try to do the thing with duality in the exercise session. So these exercises are for several weeks. So today we are going to do the duality, and it's going to look much more natural for the exercises. Sorry, I should have been a little bit more careful about that. There is a nice last thing that you can do with this phi p of s, which is cute, is, okay, I have exponential decay strictly below PC. So if I take P strictly smaller than PC, the probability of being connected to distance n decays exponentially fast. Good. What is happening at PC? Maybe there is also exponential decay at PC. Well, the answer is no. Never. And here you can see it very easily. Just let's try to prove that, in fact, the expected size of the cluster at the origin at PC is always infinite. How do I do that? So I want the expected size, so this is a remark, at PC of the size of the cluster at 0. Let's say this is the cluster at 0. So this is the sum over all the x in ZD of the probability that 0 is connected to x. And we are at PC again. Okay, let's decompose this sum by saying, well, it's the sum over n, larger or equal to 0, of the sum over the x on the boundary of the box of size n, of the probability at PC that 0 is connected to x. This is exactly an equality. Now I can turn it into an inequality by just asking here that the connections are occurring, in fact, in lambda n. What is this quantity now? Well, it's 1 over p, 1 over pc, phi pc of lambda n. So this is now 1 over pc, sum over n larger or equal to 0, of phi pc of lambda n. This is the definition. What do I know on that? At PC. So remember, I proved that PC is equal to PC tilde. PC tilde was the infimum of the P for which phi P of S is larger or equal to 1 for every S. This property of having phi P of S larger or equal to 1 for every S, it's an open or a closed property of the parameter P? It's a closed property. Phi P is obviously, P gives phi P of S is obviously continuous. So phi P of S larger or equal to 1 is a closed set for every S. So the intersection is a closed set. So at PC, I know that phi PC of S is larger or equal to 1 for every S. This, I mean, at least the first time we saw it with Vincent was really like, there is something wrong somehow. No? Whatever the critical model you take, if you take at PC, any set you can imagine, phi PC of S will be always larger or equal to 1. So this guy is larger or equal to 1 because the set of P's for which phi P of S is larger or equal to 1 for every S is closed. So if this is larger or equal to 1, I'm summing 1, so this is infinity. So I always have, this is called the susceptibility of the problem. We will see, you will probably encounter that in several other classes, including the class by Ivan. So the susceptibility is infinite at PC. And you can deduce, if you want some nice exercise, actually maybe it is in the exercises, I don't remember. If you look at, you can look at the rate of decay for P smaller than PC. Now, at which speed do I decay to 0? So let's define, for instance, L of P to be 1 over the limit when n tends to infinity of minus 1 over n. Or maybe I actually defined, let me define it. I define tau of P to be the lim nth when n tends to infinity of minus 1 over n log of the probability that 0 is connected to the boundary. In fact, you can check the limit exists. And this is in your exercises, I remember. So this is the rate of decay. This is the C. That's the real C, the best one you can imagine. Well, you can prove using this thing that, in fact, tau of P tends to 0 as P tends to PC. So you decay exponentially fast, whatever P smaller than PC, but it's a slower and slower decay. This is not a trivial statement. You are going to see that for some Potts model, it's simply false. It doesn't go to 0. This is somehow a characterization of a continuous phase transition. Good. Now, that was all I wanted to say about this. Do you have questions? I was told that I was going too fast, so I'm going slower, and now I feel like everybody is simply sleeping, which, anyway, okay. So you should really tell me interact with me if it's going too slow, if it's going too fast, if something is unclear, really don't hesitate. So computation, so now next part is going to be the computation of PC of Z2. And I should say this is the simplest computation. This exponential decay is the shortest way to get to this computation. So now that I have exponential decay, it's going to be very easy. So here, let's try first to guess what would be the PC. So for people who never saw it, what do you think about the PC of Z2? What is a natural... is there a natural guess? Let me sleep. Well, what you can see on Z2, so first you can say, okay, what is the most natural number between 0 and 1? That will be the chemist vision of it. 1/2. That's what, yeah. Then there's a physicist one, which is a little bit more evolved, which consists in saying, okay, well, look at that. If you have the square lattice, okay, I have, say, open edges on my square lattice. Let's say something like that. Well, I have a dual lattice, which is natural, which is simply, put a vertex in the middle of every single face of your lattice, and just draw edges between nearest neighbors. in this new lattice. Okay? So I have a new lattice. It's a dual of a graph. You can do that for any planar graph. We will do it for any planar graph later on. But on the square lattice, what is nice is that it is also a square lattice, this thing. Now, if I have a configuration in my original lattice, I can deduce a natural configuration in the dual lattice simply by saying for every closed edge of the primal lattice, I will say that the edge which is corresponding, you see there is one edge, I mean the edges of the dual lattice are in direct correspondence with edges of the primal lattice. So for every edge which is closed in the green configuration, I draw it blue open in the dual configuration. So I'm going to get something like that. And of course, for every edge which is open in the primal configuration, I draw it closed in the dual. So it's called a dual configuration because if you do the procedure twice, you get back to the same thing. So let me be more precise. You take Z2, you take the dual of Z2 to be just 1/2 plus Z2. So it's a shift of the lattice. So for every edge E of Z2, there is a natural correspondence with the edge E star of Z2 star, which is simply the edge that it crosses in its middle. And therefore, for any configuration omega in 0, 1 to the edges of Z2, they are in direct correspondence with the configuration omega star in 0, 1 to the edges of Z2 star, which is simply to write omega star of E star is 1 minus omega E. Okay? If the primary edge is open, the dual is closed, and vice versa. What is the law of omega star? Well, let's look at the state of an edge in the dual configuration. It is open if and only if the edge of the primal configuration is closed. So it's open with probability 1 minus p. And it's independent of the other edges because just depending on the state of this edge. So here, it's very simple to see that the law, if omega is sample according to the probability of p, then omega star is sample according to the probability of 1 minus p, of p star, I'm going to call it, where, oh no, let me first 1 minus p. Here it's a slight abuse of notation. This is not exactly this guy, it's the shift of this guy by 1/2, right? Because it's not the percolation on the original lattice, it's on the dual lattice. But let me allow myself this thing. So now, well, you want to say that there is a point which is much more natural, which is a point where the primal and the dual configuration, they play symmetric roles. So this is the point where it does that is p equal 1/2. So the theorem, and I'm going to tell you a little bit more about the heuristic after, but the theorem is going to be, and it's due to Kesten, it's going to be that PC of Z2 is equal to this self-dual point. This point where when I take the dual, I get the same model. PC equal 1/2. And we will see next week that this extends to a large class of models where in fact the natural point is not going to be 1/2, it's going to be the point for which when you take the dual model, you get the same model. And the relation will not be P gives 1 minus P, it will be a little bit more complicated. And we will get a PC which is not going to be 1/2, but which we will be able to guess anyway. Okay? So this is a theorem, beautiful theorem, and but we are going to prove it in 15 minutes, basically. Okay, thank you. Okay, let's start again. So, let's try to prove this theorem. Just as a remark here before everybody arrives and so on, is, as I promised, we had to prove that PC of ZD was strictly between 0 and 1. And this proves it because we already said, okay, PC is larger, so we have to have, we have to have PC of ZD larger than 1 over 2D. This, I told you, just count the guys, or you can just apply the last theorem to phi P of the singleton 0. And now you also have this, it's completely clear that PC of ZD is larger, smaller or equal to PC of Z2, because if you have a cluster in Z2, you have one in ZD, which is equal to 1/2. So you here, you really have between 0 and 1 strictly. And it doesn't hold for Z, but that's this you can convince yourself that PC of Z is 1. Okay, so let's try to prove this theorem. So very surprisingly, here the simple case is going to be, in fact, the hard one. At this point of the class, it's going to be very easy to prove that PC of Z2 is smaller or equal to 1/2. So let's show this inequality. But historically, I should really say this is a hard one. This is the one which is difficult. Oh, maybe I should first wave hands and see what are your reactions. Can somebody tell me intuitively why, say, PC of Z2 should be, that assuming PC of Z2 strictly larger than 1/2, so let's assume PC of Z2 strictly larger than 1/2, why this is absurd? Does somebody have an idea why? Okay, that sounds wrong, written like that. What is going to happen at 1/2? I am strictly below PC, so what do I know? I know exponential decay. So that means what? It means that my clusters in the green configuration, they are tiny, right? If I take a box of size n, the biggest cluster is size log n, right? At least this is the intuition. But now, what do I know for the blue guy? Well, I know exactly the same. The blue guy is a percolation of parameter 1/2 as well. So the cluster in the blue guy are tiny as well. But this is contradictory. If you think about it, if you have tiny green clusters, they live, they are small islands in a sea of blue. The blue should be huge. And in fact, we are going to prove that if you have clusters with exponential decay you can prove there is an infinite cluster in the dual, in fact. But this is contradictory with the fact that the dual is a percolation of parameter 1/2. On the contrary, when we are going to try in a minute to prove that PC of Z2 is smaller or equal to 1/2, if you assume it's strictly smaller, that means what? That means you have an infinite cluster in the blue guy, but in the dual, it's also a percolation of parameter 1/2, so you also have an infinite cluster in the dual. So you have coexistence of at least one green and one blue cluster. This, physically seems difficult because it would force, for instance, an infinite interface between the two. You can start to feel, okay, that smells a little bit bad. But maybe you think, okay, maybe it can happen if I assume I have infinitely many green clusters and infinitely many blue clusters. It could strip the plane. But this, we said it was impossible. We said if the cluster exists, it's unique. And that's going to be exactly the ingredients that we are going to use in the other inequality. So that was just moving hands. We are going to prove this thing rigorously. But surprisingly, the difficult part is, so there is like proof of non-coexistence of two infinite clusters. That's what I will present after. And this is, in fact, the easy part. It goes back to Harris in the 60s. So one of the first papers as well on percolation. What is difficult is to prove that, if you really don't have an infinite cluster, both in the primal and the dual. And you can already guess that it's going to be difficult because, in fact, at 1/2 exactly, it will be the case that there will not be an infinite cluster in the primal and it will not be an infinite cluster in the dual. But the big difference with when we assume that is that the clusters, they will not have exponential decay of correlation. They will not be tiny. Here, when we make this assumption, we are really making the assumption that the clusters are tiny. So let's go. Assume PC_Z2 strictly larger than half by exponential decay. And that's why it's a difficult part usually, because you need to prove exponential decay. There exists a constant C such that the probability at a half of 0 connected to the boundary of the box is smaller than e to the minus Cn for every n. So what am I going to do? I'm going to try to prove that this implies that in the dual there is an infinite cluster. What does it mean in the dual that there is an infinite cluster? Well, what you can see is, imagine I prove to you that there are finitely many circuits of open edges, of green edges, surrounding 0. Imagine I tell you there are finitely many of them. Okay, there is the first one, the second one, third one, maybe they actually intersect, whatever, you know, fourth one. But there are finitely many. This implies the existence of an infinite cluster in the dual. Why? Just take the exterior most of these circuits, take a point here outside, so it should be in blue. Take a point outside. How can it be blocked? Well, it can't, because if there is no path of blue going to infinity, that means that there is an additional circuit which is blocking it like that. So this guy that I started with, which I was assuming is the exterior most guy, is in fact not the exterior most. So this is an easy thing you can check. If you have it's combinatorial, there is no probability in that. If you have a graph with finitely many circuits around the origin, there is an infinite path in the dual. You are not blocking from infinity. So my goal is to prove that there are finitely many circuits. So I'm going to define En to be the event that there exists a circuit of open edges surrounding 0 and going through, say, the edge, the vertex n0. Okay, so I index my guys like that, and I'm looking, En is the event that there is a circuit, doing like that. I'm not assuming it's a self-forwarding walk circuit or anything like that. There is a circuit which is passing through this guy. Okay, who can give me a bound on the probability of En? A good bound. Well, to have a circuit which goes from n0 and surrounds 0, well, n0 has to be connected to distance n, right? Otherwise, it's not. So this is smaller or equal to the probability at 1/2 that n0 is connected to the boundary of the box of size n centered around him. So this is smaller than e to the minus c times n. But now there is a theorem that tells you the following. Since the sum of the probability of En is finite, there is a theorem called Borel-Cantelli's lemma. And if you don't know what it is, go on the internet to check it, because this we are going to use it very often in probability, which says if this thing occurs, then almost surely, there are only finitely many epsilon En that occur. Almost surely, only finitely En occur simultaneously. But that exactly tells you that there are finitely many circuits. Well, okay. So this bound is very simple once you have exponential decay. But here, I mean, the big downside is that if you need to prove exponential decay, you need to wait 20 years after Harris to get to Kesten, who proves this, in the case of the planar case. So that's exactly, you see, I mean, this is in 1980, so it's much before, I mean, still before the proof of exponential decay of Barsky, Eisenman, Barsky, and Menshikov. And the reason is that in 2D, you can prove exponential decay via another method. And that's what Kesten did in his paper. Okay, that was to try to. Okay, so this was one of the inequalities. So now let's prove. So assume, so thus, we have indeed that PC of Z2 is smaller or equal to a half. So now assume PC of Z2 strictly smaller than a half. What do we need to prove? We need to prove that basically the coexistence of two infinite clusters at a half is going to be incoherent. So this, here it was first proved by Harris in 1960, but there is a beautiful proof, really beautiful, by Zhang. So I'm going to present this one. So the proof by Zhang, and I'm going to put it as a lemma, because in fact, you are going to see one of the advantages that it doesn't really depend on independence. I will go back to this later. But so it's an argument by Zhang in the 90s, and which says that the probability at a half of 0 connected to infinity is 0. So this immediately contradicts this. So, well, in fact, I should not have even assumed that. I just should have said PC of Z2 larger or equal to a half follows from the following lemma. And this is the end of this proof. So I need to prove this lemma to complete the proof. So as I said, what I want to rule out is the existence, I mean the coexistence of, if I assume that this is positive, then I have an infinite cluster almost surely in the blue configuration and in the green, in the primal and in the dual configuration. So I need to prove this is contradictory. Okay, so I'm going to do, as I said, in fact, as it stands, it's not so contradictory. You have models where you can have this, but when you have this, you really have infinitely many clusters of each side. As soon as you have this kind of interface, you have infinitely many of them. So the key tool that we are going to use is uniqueness. So let me try to illustrate that. So let's take epsilon. I don't remember exactly what I need to take, so let's take it's very small, but 1/1000 is probably sufficient or something like that, but take epsilon very small. I know there is, so assume that I have this. If I have this, then I have almost surely an infinite cluster, right? Just that connected to 0, it's going to be with positive probability. So pick n strictly positive such that the probability at a half of getting that the box of size capital N is connected to infinity takes this to be larger than 1 minus epsilon. So pick n, it depends on epsilon, so that I have that. So here is going to be one thing that I want you really to mark. You put this either in your toilets or on your ceiling when you sleep, I don't know, but it needs to be in front of you all the time, is the so-called, what we call the square root trick lemma. So what does it mean? Here, I have I have this box connected to infinity. So that means that either this guy, or this guy, or this guy, or this guy is connected to infinity. outside the box, right? Because if you take an infinite cluster getting to this box, it's going to touch one of these 4 places first. What is so can somebody give me a lower bound on the probability that you hit, say, the top of the box? Well, you have 4 events. They obviously have the same probability, right, by rotational invariance. So the probability is at least, I mean, the union bound is giving you, it's at least 1 minus epsilon over 4. Problem is that 1 minus epsilon over 4, it's not very good inequality. Like it's close to a fourth, it's not close to 1, for instance. So it's not optimal. So here is the trick. And this is really, it's not specific to this proof, so you should really mark it in marble. So the trick is the following. Let A and B, so it's called the square root trick. So let A and B, 2 increasing events. Then the probability, I mean the max of the probability of A and the probability of B is larger or equal to, well, you could say it's larger or equal to the probability of A union B divided by 2. This will be just the union bound. The largest of the 2 is larger than half the probability of the union. But in fact, you can do much, much better. When you have increasing events, you can prove that this is larger or equal to 1 minus the square root of 1 minus the probability of A union B. Why is it much better? First, because I say it. And second, because here, if this probability is close to 1, then this inequality, the bound here is close to 1. So that's what you earn. Instead of having an inequality which is close to half, a bound which is close to half, it's close to 1. So this is going to be typical when you are working with events which have probability close to 1, and they are increasing. You can always use the square root trick to say that if you decompose it into smaller events of, say, same probability, all of these events, they have probability close to 1. So square root trick to remember, and the proof is simple. So you are going to say, okay, probability of A union B is 1 minus the probability of A complement intersected with B complement. Okay? Here it's 2 decreasing events. So if you have the FKG inequality for, maybe I didn't mention that. If you have for increasing events, you can deduce it very easily for decreasing events. So I leave it as an exercise. If you take 2 decreasing events, then the probability of the intersection, no, I mean, just you use it's 1 minus the probability of blah, blah, and you do the inequality, you are going to get the same inequality. It works for negatively, for decreasing events as well as for increasing events. So 1 minus this, so by the FKG inequality, so this guy is larger or equal to the product, so this is smaller or equal to minus the product, so this is smaller or equal to 1 minus the probability of A complement, probability of B complement. And this here is 1 minus the probability of A, 1 minus the probability of B. And now, what do you do? Good question. So now you just say, okay, well, okay. So you say, here, if you take the max of P of A, okay, so maybe I'm going to write it like that. 1 minus the probability of A, 1 minus the probability of B is larger or equal to 1 minus the probability of A union B. So now the 1 minus the max, 1 minus the min, no, okay, the max of 1 minus probability of A, 1 minus probability of B is larger or equal to square root of this. And then you deduce your inequality by just translating. So there is a problem with mean, right?
Yeah, the last inequality should be there.
Thank you. I told you that I would, yes, okay. Now it's much better. So the mean, and I don't have to cheat and say, okay, now you finish the thing, I can do it. So it's 1 minus the max of P of A, P of B, which is, yeah. You know, I mean, when you are just in front of the board, it's so close, this thing. It's so black that, it's not so easy to see your own mistakes. So thank you for being there. Okay. So remember, notice if I take 10 events, what am I going to do? If I take 10 events, here I'm going to get 1 minus the probability of the union to the power 1 over d. This is really the same computation. So here I have 4 events. So what do I deduce? I deduce that the probability at a half of this guy connected to infinity without using the box, really in the outside of the box, is larger to 1 minus epsilon to the 1/4. That's what I get. So the probability at 1/2 of the top connected to infinity and the bottom connected to infinity, maybe by the same guy, I'm not saying that they are disjoint paths, is larger by the FKG inequality, is larger than the square of this guy, which is larger, okay, so. Larger than that, okay? Take this quantity to be strictly larger than a half. So let's take even like 3/4. So you see, you can try to deduce what is the best epsilon here. So if it's larger than a half, what can I say? Well, I can also say, okay, then with probability, I mean, what is the probability of this guy then? I want these guys to be connected to the top and, I mean, have a connection here to infinity. I have a connection here to infinity. But I can also, so this happens with probability 3/4. But with probability 3/4, I also have that this guy is connected in the dual to infinity and this guy to the dual to infinity. Because it's also a percolation of parameter a half. So this is perco-dual. So it's not perco-dual, it's dual perco, sorry. With parameter half. So therefore, it has the same probability of occurring. So this is larger than a half. The probability of the intersection of two events of probability 3/4 is a half, at least. Here I cheated a little bit because it's in the dual. So you know the dual box is maybe shifted by 1. This is really, you can fix it in 10,000 ways. Let's not focus on that. It's not relevant here. Now, what is contradictory here? Do you start to feel that, okay, this smells bad or good? Depends on whether. How do you conclude here? You conclude with a uniqueness, yes, but how? I mean, what do I need to do to really convince you that this is now in contradiction with uniqueness?
Filling the box.
Yeah, look what is happening in the box. The box here, I said, you know, I'm connected to infinity, but I didn't need to know what is inside the box. So what I can do in the box is close everybody. Let's close everybody. All the edges in the box are closed. So this costs me what? It costs me 1 minus p to the number of edges in my box. This is strict positive, but this event now is included in the event that there are 2 infinite clusters. I mean, at least 2. I mean, in particular, there are 2, which is 0. And this is contradictory. Okay? Here, what is nice with this proof is that somehow it doesn't really use independence except at this very last step where we say in the box we close everybody. But you are going to see that there will be a property weaker than independence that will allow us to do that, which will be what we call the finite energy property, and which is valid for a very large class of models. So this proof is going to extend very easily. Good, so that was the proof of Zhang's argument. So in particular, there is, so therefore, we have concluded PC is equal to a half. And notice that we did something more, which is cute. We also proved, so we proved, well, that the probability at PC of 0 connected to infinity is 0. So I was telling you, maybe it's not so clear that at 0 there is no infinite cluster. Well, on Z2 we proved it. So this is on Z2. And once again, this is completely open in general. And that's maybe one of the main conjecture in probability, is to prove it, say, on Z3, which is the physical dimension. Yes?
Say you didn't rely on independence at all. We still use the square root trick, so we used FKJ, and the proof we saw for FKJ used independence.
Exactly, but we will prove FKJ inequality for dependent models, for a large class of dependent models,
but what
not
do you
using
expect
independence.
of such a model to satisfy FKJ?
Yeah, there are many more models that have the FKJ inequality than the independence. Independence of FKJ and monotonicity are really two different properties.
But what do I expect of a model for it to have FKJ?
What do you need to expect? This I will answer next week,
okay,
because we are going to exactly spend time on that. Yes. Okay. So now we know that PC is a half. What do we want to do? Well, we want to study what is happening at PC a little bit more. So this is the next step. And that's going to be a very important step, which is study of the Rousseau, Seymour, and Welch theory. So we know, notice, at PC, we know there is no infinite cluster, and there is therefore no infinite cluster in the dual as well. So this argument that we used to prove that PC couldn't be strictly larger than a half, well, here it doesn't work. And it's not contradictory because, well, we needed to prove that the sum of the probability of the event En was finite, that we had only finitely many circuits. And for that, we use the exponential decay. But the exponential decay, we proved, was not holding at PC. So in fact, at PC, we are going to be able to prove there are infinitely many circuits, and also infinitely many dual circuits. So you have this kind of circuit which alternates, dual and primal. So what we are going to, it kind of tell you that if you take a big box, whatever the size of the box, well, there are going to be open paths crossing it and dual open paths crossing it with basically positive probability. So the theory of Rousseau-Seymour-Welch exactly tells you that. If I take a shape, a box, say, or rectangular box, then the probability of having a crossing from left to right is not tending to 1, not tending to 0 when the size of the box varies from 0 to infinity. That's the content of the Rousseau-Seymour-Welch theorem. So in order to really start working on this thing, let's define a few things. So rectangle R is just going to be a guy of this shape. And it can be a rectangle in the primal lattice. I can also take it in the dual. Usually when I work with it in the dual, I'm going to put a star here, and these guys are half integers instead of being integers. Okay? So here it's A, B, C, D in Z. And if it's going to be that if it's dual. I'm going to define CV, so vertical crossing of R, to be the event that, so I say, no, horizontal, let's start with horizontal. The event that A, horizontal, sorry, A times CD is connected to B times CD in R. So it's just the event. I take my box R, And it's the event that have a path from this to this, staying in R, okay? The important thing, it has to stay. It cannot go up or down. It has to stay in R. And you define the same thing with vertical to be the event where you understand it's going to be the event which corresponds to this event. And you can define this in the dual as well, okay? So then in the dual, I will put things like that. So the Rousseau-Seymour-Welch theory, which is at the base of many, many results that we are going to get on the critical phase, is the following result. For any rho larger than 1, that's 0, there exists a constant which depends on rho only, such that for any n, if I look at the probability at one half of having a horizontal crossing, actually let me just draw them. I don't know why I actually, let me draw it. N by rho n box having a crossing like that. Maybe I will use this a little bit later, but so far let's just draw because we are on the board. This probability is bounded uniformly away from 0 and 1. It doesn't tend to 0, it doesn't tend to 1, whatever the rho. And notice that this is a property which is very, very specific to PC. So I let you think, so if P is smaller than a half, well, you have exponential decay of probability that this guy is connected to distance n. So since you have only n guys here, the probability of this crossing is going to also decay exponentially fast. You have exponential decay, in fact. And I let you think why when P is larger than a half, it tends to 1 exponentially fast. So it's really a property which is specific of the critical point of 1/2. Here I'm going to just prove it in the simplest case of Z2, and I'm going to give you the latest proof and the shortest one. Because anyway, we are going to prove it in a more general context later on, and the proof will be more conceptual. If I have time. I don't know if I will have time to do it. But I should say that if you take another lattice, I don't know, take triangular lattice, hexagonal lattice, whatever lattice you want, planar, pick PC. PC has no reason to be half in general, so it's not going to be half. But at PC, you will always have this property. So this is not, here I'm going to use a half because I'm going to use the self-duality between the primal and the dual, but it's just to prove to you a nice, to do it in the cleanest way or in the neatest way, but it's not at all necessary. Like if you look at more general arguments, then you get it, in fact, for any critical percolation model. So it's a very conceptual proof. The general one. Very well. Let's start with rho equal 1, because in general, when you see this theorem, people tell you it's completely obvious. Rho equal 1. Let me actually cheat a little bit. Let me look at the probability at 1/2 of this event. You take n times n plus 1, and you look at the probability of crossing like that. I should have used blue. Do you have an idea what this is equal to? But now look at the boundary of this guy. Look at the boundary of this guy. There is this blocking surface which is going along the boundary, the right boundary of this guy. This is what? It's exactly a crossing in the dual configuration from top to bottom. Okay? So the complement of this guy is the probability at a half of having a crossing from top to bottom. So be careful because here you really need to block. So in fact the guy is starting like 1 point above, like 1/2 integer above, and it's ending 1/2 integer below. So in fact this guy, so there is a dual crossing. So if I don't have this event, then that means I have this one. And notice that here it's really in this box which is like that. Okay? But this is also a n by n plus 1 box. So by rotation, this event, because it's dual at 1/2, it's just percolation of parameter a half. So this guy has the same probability of this, and because these were complement events, this was equality 1. So this thing is exactly equal to a half. So for any n larger or equal to 1, the probability at a half of having, so okay, n times n plus 1 like that is exactly equal to a half. There is no freedom. So okay, this part is not so complicated, right? So you really think, okay, well, then I'm done. You know, I mean, it's going to be easy to conclude because this already gives me the lower bound for any row smaller or equal to 1. And it gives me the upper bound for any row larger or equal to 1. Because the upper bound, you get it from the lower bound, right? This I should also say. So this was the first remark. The second remark is that probability at 1/2 of n rho n of this, well, we said it's 1 minus the probability at a half of n rho n, but having a guy like that. So this is smaller or equal to 1 minus c of 1 over rho. Right? For this guy is just percolation, but here the aspect ratio is 1 over rho. So it's sufficient to get the lower bound. So it's sufficient. So I have the lower bound for any row smaller or equal to 1. I only need to get the lower bound for row, for any row. And also notice that if I pick a row larger than 1, then if I want, say, the probability, can I get a lower bound on the probability to have, say, n times, so let's take rather alpha larger than 1, 0. Can I express the probability of going to distance 2 alpha, to having this guy, just in terms of crossing of the probability, I mean, of guys that go to distance 1 plus alpha. I mean, aspect 1 plus alpha, aspect ratio 1 plus alpha. Another way of saying is, because was not very clear, imagine I give you a lower bound for 1 row larger than 1. Can you deduce it for any row larger than 1? So if I want to cross like that, what I can do, I can just use the fact that here I have one rectangle of aspect 1 plus alpha, aspect ratio 1 plus alpha. I have a second rectangle of aspect ratio 1 plus alpha, which is here, which I'm going to draw in green, no, in pink. I have so many colors, it's great. So if I want to have a crossing from left to right, I can say, okay, maybe I have a crossing like that, I have a crossing like that. Well, these two guys, they have no reason to intersect whatsoever, right? So if I assume this orange rectangle is crossed and the pink rectangle is crossed, that doesn't imply at all that the white rectangle, the big rectangle, is crossed. But if alpha is larger than 1, here you notice I was very careful. So here, this rectangle, what is its aspect ratio? It's just 1. This is a square. So how can I be certain that this guy is going to intersect this guy? Exactly, I can just assume that this white square is crossed from top to bottom. Okay? So this is always going to be larger by the FKG inequality. I mean, so if I want a crossing from there to there, I can assume there is this, and this, and use the FKG inequality to say that this is larger. Well, I use twice a crossing in an aspect ratio 1 plus alpha. And I use once a vertical crossing of a square. So if all these guys are positive, I'm going to get a positive lower bound for the other one. So I can always assume that C of 1 plus 2 alpha is larger or equal to C of 1 plus alpha squared times C of 1. And this, you agree, will tell me that if for any alpha positive, I'm able to prove the lower bound, then I have it for every alpha positive. Okay? Just for you to try, I mean, why not trying to do the same reasoning, but this time with, I mean, let's say we really want to express everything in terms just of C of 1. Let's not assume that we need an alpha positive. Let's try to do it from C of 1 directly. So then, okay, you take a box which is slightly longer than C of, so it's n times n1 plus epsilon, and take epsilon tiny. And let's try to do the same. So you take a box of size n times n, and you say, well, this I know that with probability of half, I cross this guy. Good. Okay, I want it to go a little bit farther. So let's take a box of size n like that, and let's say, I mean, a square like that. Let's say this is connected to there. Okay. Now what can I have no guarantee these guys are connected. So it could be, that with probability a quarter, you have a crossing of this box, a crossing of this box, but that with probability tending to 0, you have a crossing of the big box, because maybe these two guys, they don't like each other and they try to avoid each other. Intuitively, it's completely wrong, and indeed it's completely wrong, but you cannot really exclude it a priori. So then you can say, okay, well, I can take this square and say it's crossed from top to bottom, say. Okay. Oh. This guy has no reason to come and intersect these guys. He's going to necessarily intersect this one, but this guy is no reason. So you say, okay, maybe I take a box a little bit more centered. That would be smarter than doing that. Because here, maybe it's simpler to intersect, but there the guy can do like that. Maybe, okay, so maybe I wanted to take a box like that. Like that, I'm really certain that, so let's forget about this one. I'm really certain that the guy is going to intersect these two paths, right? If it's like that. So it seems like I won. But why this guy didn't do like that? This guy, I mean, he had the right to do like that. He had no reason to stay in this small box. So basically, all the drawing you are going to do with these things are going to be insufficient to solve the problem. And and you can easily convince you that there is something non-trivial by just thinking, imagine the model is, it's doing something very strange. It's basically always drawing paths in the diagonal. Imagine that very naturally the model, in fact, the clusters in the model at criticality, I mean, I have no reason to believe this is going to be the case, but they all look, very much like that. Very, very much like that. So then squares are basically crossed with probability of half, because it depends whether this guy is going to end up just there or just here, there. But it will never cross long rectangles. And you can imagine with model with a little bit less symmetry that this could happen. And we actually don't know in these cases how to rule it out. So here we are going to use symmetry to try to say that we don't have something like that. And we are going to use the independence to try to prove this. So just a proposition we will prove next week is the following, is that in fact the probability at a half of crossing, so let me see how I wrote it, and then I release you, of crossing a minus n, and here I'm going to put minus n 2n, so it's a, so this is a 3/2, I mean the aspect ratio is 3/2, the probability of crossing like that is larger or equal to 1/128. Whatever the constant, just that we are going to get this one. So this is the end of the class. Just two things. The first one is I will be away for 2 weeks in a month in order that we don't miss too many classes. There will be somebody replacing me, but what we can do is next week, normally there is no class because it's called Dies Academicus. I don't know why they do that, but anyway. So what I propose is that we do a class next week. So let's do a class next week, and like that you will have a class free probably the last weekend of October, the last Friday of October. And the other class, Matan will replace me. Like that, it's just he replaced me for one class. Yeah, that's you. Okay, thank you. And for the guys from the master class, I will come back in an hour and we discuss the repartition of the articles. Okay? Thank you very much.